Okay, good afternoon, everybody. So I am Lucas from the Antwerp Young Minds. I'm happy that you're all here. So I will quickly, for those who don't know, introduce the Antwerp Young Minds. So we are a group of PhD students and we organize activities at the Department of Physics. And these include workshops, field trips, but also the departmental colloquia like we have today. And this will actually be the last activity of this semester, so I don't have anything new to advertise to you. But if you want to, in the future, stay up to date, then you can follow us on social media. So I recommend it. I don't have the QR code with me right now, but it's only a Google search away, or your favorite AI chatbot can probably tell you as well by now. So, okay, please follow. So that's that. Now, by now, you probably noticed that my hair is a bit wet, and that's because I arrived exactly when the weather was worse. And so actually, if I had checked the weather forecast before, I could have avoided it by coming 10 minutes early, but I didn't. So let that be a warning for all of you. You should take weather forecasts seriously. And so we have another person here who takes weather forecasts seriously. He's in fact a professor in Ghent, but also connected to the Royal Meteorological Institute. And so he knows all about how to model weather, how to model our climate, which we can call atmospheric modeling. And so I could tell more, but I think it's better if I let him take the words. So an applause for Professor Steven Caluwaerts.
Okay, thanks a lot for the nice introduction. I'm very happy, first of all, to be here in Antwerp. For me, it's the first time that I am at this campus, so that's maybe a shame, but I have been here at the university, but always in the city center, never here. So it's a nice first for me to be here. I am indeed working at the Royal Meteorological Institute in Uccle and also at Ghent University. And I have a research team that is doing research on atmospheric modeling. So I have chosen to talk today about the miracle of atmospheric modeling. Why miracle? This is maybe a bit subjective, but at least in my opinion, it's actually quite a miracle that we are able to forecast the weather days ahead. And also climate modeling is quite a complex topic. And so it is really quite an achievable, let's say, that we are able today to do this kind of modeling of the atmosphere. And I would like to convince you about this, and I have decided to make 3 parts in this talk. I will first talk about the past, about the history of weather and climate modeling. Then I will talk about the present. Where are we today? What do we do today? And then I would like to finish with a few trends that I see for the upcoming years and decades about weather and climate modeling. And from time to time, I will try to make the link with research that is going on in my group or in other Belgian research teams. So this talk will be an introduction about atmospheric modeling. If you have very detailed questions, if you would like to discuss about, I don't know, the equations, we can do that after the talk. But here I will try to give you a broad overview of what we are doing and what the challenges are. Let me start with a weather map. And this is a weather map that shows the situation over Europe last Thursday at midnight. So it's what we call an analysis. So it's the situation last Thursday at midnight. The black lines, they give the mean sea level pressure. So you recognize a high pressure region over Eastern Europe, a low pressure system between Iceland and the UK. And then the colored lines, they are a measure, or they show regions where there is a significant wind. This was last Thursday. If I would ask someone in the room to guess how the situation would evolve the coming hours and days, I guess no one is able to tell me what will happen with this low pressure system and this high pressure system, because it's a very complex actually. I'm also not able to, let's say, predict by eye how everything will change. This is really very challenging. So last Thursday at midnight, the weather computers of the European Center for Medium Range Weather Forecasting started their forecast, and they came with this forecast for today. So this is the situation forecasted 6 days ago for today, again, midnight. So now we have a low pressure system over Scandinavia and a northwestern flow over the Benelux. So we have probably, well, this is a weather map that corresponds with cold conditions, so quite cold air, and typically we will have a lot of showers when you have this. And of course, by now you came by bike or by foot or by public transport, you probably discovered that indeed it's quite showery today. And if we compare the forecast of 6 days ago with the real situation now, then you see that it's of course not identical, but the forecast was not too bad. So this idea of the northwestern flow, this low pressure region over Scandinavia, that became reality. So this is just as an introduction to show that actually today we are able to look quite a few days in the future with reasonable performance, I would say. And the question is, how do we do this? What is behind these weather models? How does that work? And I will explain you that during this talk. From time to time, I will also make the switch to climate modeling. Climate modeling, which is a completely different problem, but at the core of climate modeling, you have again the atmosphere. So the laws of physics, they are still the same. The physics that is driving the motions in the atmosphere is not changing, but the way that we use climate models is completely different than weather models. And I will explain you that, and I will later come back on this kind of figures. So what is behind this? How does it work? Where is the magic? And let's have a look. And let's first dive into the past, because the history of weather modeling is quite an interesting story. And weather modeling has a long history. Actually, already in ancient times, people were interested in the weather, because the weather has a huge impact on your daily life. When you are a farmer, you are interested in whether it's going to rain. If you have a dry season, then your harvest will be very poor, and so on. So already in ancient times, already in the Bible, for example, you see quite some weather statements popping up. So people have always been interested in the weather. And one way to illustrate this is to have a look at some weather sayings, weerspreuken in Dutch. So a few years ago, there was this Flemish weather forecaster, Geert Nasus, and he wrote a booklet full of weather sayings. And I dived into that booklet for the presentation today. And I would like to show you that actually already quite long ago, people were trying to understand the weather. So people long ago, they made observations of the weather. They have written in books the weather every day, and they try to learn something from these observations. For example, there is this weerspreuk, regen uit het oosten, 48 uur zonder vertroosten. So people observed that if it's raining, if the rain comes from the east, then it can rain for quite a long time. And actually, they didn't understand the science behind that, but it's true. For Western Europe, we typically have our weather coming from the west, like today. And if you are in that situation, then everything is going quite fast. If you have a cold front, then after a few hours, it will be dry again. If rain is coming from the east, that's quite exceptional for Belgium. But if that is happening, then typically we have this kind of blocked situation. And then you can have rain for a long time. And one recent famous case are the floods in July 2021, when the rain was coming from the east, and we all know how that ended. And so people didn't understand the science, but they observed this. And this is a weather saying for today. So the 13th of May, some of you might remember that we have these ice saints, the ijsheiligen. So these ice saints. En dan er is de weerspreuk, servaas moet verlopen zijn, alvorens nachtvorst goed en wel verdwijnt. So people saw, farmers discovered that actually the first half of May, quite often there was still some freezing temperatures. And then in the second half of May, this becomes quite rare. And so you have these ice saints weather sayings. So there was always an interest in weather, but of course, people did not really understand here how it was working. And that changed during the 20th century. And a first breakthrough for weather modeling happens in 1904. And then we have this person, Wilhelm Bjerknes. He was from Norway. And he was a physicist. And he stated that based on physics, it should actually be possible to make a weather forecast. And he has written a paper in German. I show you the English translation of part of that paper. And what he says is that if we know the current state of the atmosphere, if we know the weather now outside, and if we know the physics that is driving the motions in the atmosphere, then it should be, in theory, possible to make a weather forecast. So he was the first who came up with the idea of trying to predict the weather based on physics. And this person, he did not make a weather forecast, and he just had the theoretical idea, let's say, but he was quite optimistic that one day it would become possible to make this kind of forecasts. And he was optimistic because in 1904, they were starting to collect more and more observations about the weather. But all these observations at that time were over land. We had no information about what happened over the oceans. And also we had only information close to the surface. At that time, we did not have satellites yet or balloon soundings, okay, somehow, but we did not have planes, satellites. So the information was limited to the surface. But he understood that with technological advancements, one day it would become possible to have a global picture of the atmosphere. And for the second part, the laws of physics, actually, they were already well understood. So the physics that is driving the motions in the atmosphere, that's just the traditional fluid dynamic physics. And that's conservation of momentum, conservation of mass, conservation of energy, ideal gas law. So these equations, that's old school physics, that's quite standard physics, that was known already at that time. So this is a very interesting document because for the first time, a person advocates that it should become possible to make a weather forecast. And then about 20 years later, there is this person, a person from an English scientist, Louis Fry Richardson, and he made the first weather forecast. And so what did he do? He took the work, he read the work of Bjerknes, so of the previous person, and then he took these equations and he tried to solve these equations. But the problem with the equations is that there is no analytical solution. So you need to use techniques to find an approximate solution for the equations. And so he applied a technique that we know today as finite differences. So he discretized the partial differential equations with finite differences. And then he made a set of equations that you could use to solve the weather, so to say. And Richardson, he said, okay, so first he derived all the equations that he needed, and then he took the challenge to make an actual forecast by hand. So what did he do? He has written all the equations, and then he tried to make a forecast for one particular location for the next 6 hours. And his aim was to forecast the change in pressure for the next 6 hours. So not very ambitious, only 6 hours in the future, one location. And the result was dramatic. So this person has been calculating for 2 years, so by hand, and he came up with an increase in pressure of 145 hectopascal, which is complete nonsense. So he had done a lot of work, and the answer was complete nonsense. So that was a huge disappointment for Richardson. And later, scientists, they had a look at what he exactly did, and actually his equations were correct. So the mistake was not in the equations, the mistake was also not in the computations, but the problem was in his starting point. So there was what we call a poor initialization. So his starting point, there was a problem with that, and that led to a forecast that was blowing up. He published his work, but his book was not very successful because actually it was a failure. But nevertheless, we see him today as the father of weather modeling, because he was the first to really try it, and actually his trial was a very good one. But in his book, he also writes down his fantasy, his dream, his vision. And there is a part where he describes a so-called forecast factory. So Richardson understood that, of course, doing all these calculations by hand and needing 2 years to calculate the weather forecast for 6 hours for one point is not very useful. So he said, after so much hard reasoning, may one play with a fantasy? And then he describes a theater where he collects thousands of people, and all these persons become computers. So they all have paper and pencil, and they will all make calculations together. So here we have a very small theater, let's say, with computers. But he said, if I have thousands of people, bring them together, and they all do computations, then it should be possible to make a weather forecast that is in time. So that was his dream, that was his vision, and here you see an artist's impression. And of course, this vision of all these computers, but he meant people doing computations, that's exactly how a supercomputer looks today. And today we have a supercomputer where we have millions of cores all doing calculations in parallel. So he described this kind of forecast factory, but the computers were, of course, people at that time doing calculations. So he was a very visionary person. And this Richardson was really an interesting person, because all the science that I describe here, he did that during the First World War. He was a volunteer in France for the ambulance. So he was working at the front. And while he was there, he was doing these calculations and making this first weather forecast. So very interesting person. And then there is a third important moment, and that's in 1950. Because in 1950, we have a paper with the title Numerical Integration of the Barotropic Vorticity Equation. And in this paper, they describe the first weather forecast with an electronic computer. So here you see a picture of the ENIAC, the first computer developed at the end of the Second World War in the US. Von Neumann was involved. Von Neumann was one of the drivers behind the Manhattan Project, the development of the bomb. But he was also involved in another project that was called the Meteorology Project, the Weather Forecast Project. He collaborated with a few meteorology people, and together they implemented this idea of Richardson on this ENIAC. And this time the results were quite successful. This time it was not a disappointment. The weather forecast that came out of this ENIAC machine was actually not too bad. And there are, of course, still many limitations. They used simplified equations. They did not solve the full set of complex equations. They used so-called barotropic vorticity equation. They had a very coarse resolution. Here you see their domain. So their weather forecast was for North America, but you see that the grid points where they did the calculations, they are far away from each other, so very coarse resolution. And their forecast was still very slow. It took them 24 hours to make a 24-hour forecast. So they were not yet in time to be actually useful. But von Neumann and colleagues, they write somewhere in the paper here that they are waiting on a bigger machine that they are building, and with a bigger machine it would become possible to do it in 30 minutes and so on. So here, this is really a first successful numerical weather forecast. And after this paper, other countries, other research teams, they start to invest in this. And a few years later, Sweden will be the first country that comes up with operational weather forecasts on computers. So this is the history, let's say, of weather prediction. One final moment from the past that I would like to draw your attention to is 1967, because in 1967 there is a famous paper written by Manabe and Wetterald, and Manabe will then in 2021 receive the Nobel Prize in Physics for this work. So Manabe was actually the first one who he pioneered with climate models. He was the first one to make a simple, successful climate model. And in 1967, he presented a one-dimensional model. So it was just one column of air, and he implemented all the physics that is needed to understand the impact of a changing greenhouse gases on this column of air. So he had all the radiation equations and also convection in his model. And with his very simple one-dimensional model, he made an estimate of what would happen if the CO2 content of the atmosphere would double from 300 parts per million to 600 parts per million. So if you double the CO2, then he found that you would expect an increase of about 2.5 degrees Celsius. And this is what we call the climate sensitivity. And actually, this number did not change a lot since his paper. And today, we have far more complex climate models, three-dimensional models, where we have many components. I will come back on that. This is really a very simple model, but what came out of his very simple model was already a very good estimate of the climate sensitivity for CO2. So he got a Nobel Prize for let's say, the initiation of climate models. And so this is about the history. And now, important, where are we today? What is the situation today of atmospheric modeling? Well, today we can do quite a lot with these models. And I would like to demonstrate this with this picture. So here, this picture of planet Earth is a very famous one. It's called the Blue Marble. It was taken by Apollo 17. And it's a picture where you see the Earth in sunlight. And you can see on these famous pictures lots of meteorological phenomena. You have fronts, you have over Africa, you have a lot of convection, thunderstorms, and so on. So you see that at different scales, you have cloud patterns, very complex. 50 years after taking this picture, the Germans, they wanted to, let's say, recreate this picture, but this time with their global weather model. So here, the second picture is output of the German ICON weather model that is run at 1 kilometer resolution over the globe. And you can see that actually by eye, you cannot say which one is the model and which one is the picture. So you see that our weather models today, they are really very, very realistic in the way that they can represent all the motions in the atmosphere. So this is just a demonstration of the capabilities, let's say, of the models today. You cannot see the difference anymore between what comes out of a model and a real satellite image of our planet. Of course, this does not yet mean that we are able to make good forecasts, but this is demonstrated on the next slide. So here you see the scores of our forecasts. If you make a weather forecast, weather forecasting is actually quite easy if you compare it with climate. Because if you make a weather forecast for tomorrow evening, we know whether it was a good or a bad forecast. If you do climate simulations for 2100, I will be not only retired, but I will be probably dead by the time that we will have the results of this experiment. So climate modeling is in some way harder because you don't have an immediate observation to compare your experiment with. But for weather you do have, and then you can easily calculate scores. And on this picture you can see the progress in our weather forecast. So here we start in 1986 till 2025, and here on the vertical axis you have a score. The higher, the better, and 90% is obviously a better score than 50%. This score expresses how well the predicted 500 hectopascal geopotential height corresponds with the real 500 hectopascal geopotential height. What does that mean? Well, actually 500 hectopascal geopotential height, that is the height in the atmosphere where the pressure will be 500 hectopascal. So at the surface, it's close to 1000 hectopascal. When you go up, pressure decreases, and at about 5 kilometer height, you have 500 hectopascal. And this field tells you a lot about the broader scales, about the synoptic situation. So it's one of the most popular fields, let's say, for our weather forecasters at the Met Service. And then you see the scores, and the yellow scores are the scores for the forecast 10 days in the future. Initially, these scores were so low that they are not yet on the graph, but since 2000, we have scores that start to reach a little bit higher levels for 10 days. Green is 7 days, red 5 days, and blue is 3 days in the future. And if you then, for example, use this stick and put it at a score of 80%, then you can see that around 2000, we reached this 80% for the forecast 5 days in the future. Today, we reached the 80% for the green one, that's 7 days in the future. So we typically summarize this as every 10 years, we gain 1 day into the future. So we can look 1 day for the same accuracy, 1 day further into the future. And that's quite a spectacular performance. So weather modeling is or has been improving. Why did it improve? What is the main driver of the scores that improve? What do you think? Yes, computational power. And there's a second one, that's our knowledge of the atmosphere. So now we have lots of satellite information and so on. We have a very good picture of the planet. Every minute we collect millions of data, and this improves also a lot of forecast. And then the challenge of researchers like me is to make sure that these lines continue to increase in the coming decades. And that becomes harder and harder for some of these scores. Okay, the weather model. Here you see a few equations, and you all know them. Well, if you study physics, you should know them. So here you see actually the equations that form the core of a weather model. You have the 3 components, X, Y, and Z component of the conservation of momentum, where you have the acceleration, and then in the right-hand side you have the forces in the atmosphere. The pressure gradient force is important, gravitational force for the vertical direction, and then these terms, they are the Coriolis force, and they come from the fact that the planet is rotating. Then we have conservation of energy, conservation of mass, and the ideal gas law. And these 6 equations, they actually form the core of the weather model. They describe all the motions in the atmosphere. And the problem is that there is no analytical solution possible of this set of equations. So you cannot write down the solution. You need to go to modeling techniques. You need to discretize these equations. You need to make choices to solve them then in a numerical way. And the different modeling groups in the world, they make all different choices and they end up with different weather models. So this is the core of a weather model, but of course there are many other things that you need. This is the backbone. In the end, you end up with quite complex models. For example, the weather model that we use in our institute has a code of more than 1 million lines. So it's Fortran code. It's still very old Fortran code, and it's over 1 million lines of code. So it's not very trivial. The weather models are complex, but this is at the core of these models. How does it then work? Well, assume that we would like to launch a weather forecast, and we would like to start at 12, so a few hours ago. First, we need to take the globe and we need to divide the globe in lots of grid cells or grid points. And here, let's take as an example the weather model of ECMWF, and the European Center for Medium Range Forecast. That's generally considered as the best meteorological center of the world. Their main model, IFS, has a resolution of 9 kilometers. So every 9 kilometers, you have a grid point on the Earth that results in 6 million grid points. But then you also have 137 vertical levels in the model. So if you multiply these two, you are quite close to 1 billion of points. So in each of these points, you need to solve all the equations. But first, you need to collect the initial state. So every second, we are collecting lots of observations from planes, ships, satellites, balloons, weather stations, radar, and so on. All this information is collected for the globe. Based on this, you can create a starting point for your forecast. So we make a starting point, and then we can time step with our model in the future. And for example, the IFS model has a time step of 7.5 minutes. So every time that you do one time step, you are 7.5 minutes later. Of course, if you want to make a forecast for the next 10 days, you need quite a lot of time steps. So this blue arrow, the time stepping algorithm, should be as efficient as possible. And for example, for my PhD, I worked for 6 years on making this time stepping more efficient for the model that we are using in Belgium. So this is a lot about numerical techniques, numerics, and also about the computing systems that you use. And in this way, you can do more time steps, and in this way, you can make a forecast for the coming hours, days, or weeks. So this is how it works. Then you need a supercomputer. Here you see a picture of Lumi, which is one of the machines that we are using in our group. So it's a Finnish, it's a European machine located in Finland. When it was launched, it was the biggest supercomputer of Europe, but today, because it's going very fast, it's only number 4 or 5 in Europe. So you have 2.7 million cores. Richardson would say 2.7 million computers. You have 531 petaflops. So one flop is one operation per second. So you have 531 peta. Anyone who remembers peta? What does it stand for, peta? 10 to the 15th, indeed. So 531 times 10 to the 15th operations per second, and it's consuming 7 megawatts energy. This energy consumption is not a detail, especially if you're doing climate simulations. You don't want to be part of the problem while you're computing the solution, so to say. So it's not only about having the biggest supercomputer, it's also about having a supercomputer that is not too dirty, let's say, and where you can pay the electricity bill. So this is Lumi. And today, just for your information, there is this top 500. Every 6 months, there is a new update of this list. The number 1 today is an exa scale machine. So now we are at the 10 to the 18th flops per second. Okay, so computing power is important. The bigger the machine, the more complex your model can be, the more computations you can do. And then it becomes important to think about this diagram. So what do you see here? You have a horizontal axis where you have spatial scales from 20 meter to 10,000 kilometer. And then you have a vertical axis where you go from 1 second, 1 minute, 1 hour to 1 month. And then you have different meteorological phenomena. For example, a hurricane has a typical spatial scale of about 500 to 1,000 kilometer, diameter 500 to 1,000. And it lives for something like a week on average, a hurricane. If you have a weather model at 9-kilometer resolution, it's clear that you will be able to resolve these big hurricane systems. That will not be a problem. But for example, if you go to thunderstorms, some of you were in a thunderstorm just before the lecture. Typical spatial dimension of a thunderstorm is about 10 kilometers. Typical lifetime, 1 hour, 2 hours, depends a bit. But spatial scale of 10 kilometers, a model at 7-kilometer resolution, remember here, or 9 kilometers, sorry, 9-kilometer resolution, 10-kilometer scale, then you will not be able to resolve very well these thunderstorms because your model is a bit too coarse to really capture them very well. So here you have already a bit of a problem because forecasting thunderstorms is quite important. The people expect that we can forecast a thunderstorm. So this becomes a bit tricky. And then, of course, if you go to smaller scale phenomena, like turbulence or the formation of raindrops, that's micro scale, that's micrometer scale. If you go to these phenomena, it's clear that we cannot really resolve them with our models. So everything that is too small to be resolved will be parameterized in our weather models and in our climate models. And these parameterizations, they form also an important source of uncertainty in our models. So ideally, we would be here with our resolution, but we cannot afford that with the current computing power that we have. Of course, you can do a small trick. Instead of forecasting the weather for the whole planet, you could zoom in on a certain part. Assume, like the RMI, we are only interested actually in Belgium. That's our task that we have from the government. So we could focus on Belgium, we could focus on Western Europe. If you zoom in on a certain region, then you can go to higher resolutions for that region. But the problem is then that at the border of your small domain, you need to have information that comes from a larger scale run. And this also creates some numerical challenges. That's not straightforward. But for example, at KME, the RMI is running everyday forecasts at 1.3 kilometer resolution. And at 1.3 kilometer, this thunderstorm that you had before the lecture is perfectly resolved. This model will do much better for thunderstorms than the global model at 9 kilometer resolution. A final point that I would like to make about weather modeling today is that our atmosphere is very complex, non-linear, chaotic, and after a few days, a weather forecast typically becomes poorer and poorer. And to assess the uncertainty of our weather forecasts, we use a special technique that we call ensemble forecasting. And here is a demonstration of this technique. So what do you see here? Well, we are the 24th of December, 1999, and 1 day later, France, and then 2 days later, Germany will be hit by a very important storm, winter storm, that will result in significant damage. But at that time, that storm was very badly, very poorly forecasted. And what you see here is the starting point of the weather forecast on the 24th of December. And you do not really see a storm yet, because there wasn't a storm yet. And then you also see 50 other copies, you could say, from this initial state, but each of the 50 is very slightly perturbed. So there are very, very small changes in each of the other initial states. And then we run the model, and our original forecast did not forecast a storm. So we missed the storm. This is what happened in reality. You see a very small but significant storm system over France. And here you have the 50 other forecasts. So you do not see a difference in the starting point, but only 42 hours later, you have really very big differences in the forecast. So this was a very quite unique situation because there was this very explosive atmosphere that was able to create this kind of storm system. So that's quite rare. But you can see that very small changes in the initial state have a huge impact on the forecast. Forecast 13, 24, 48, all very big, strong storms. So what we do today is, by default, we run the model 50 times with slightly perturbed initial states. And then we can also have an idea about the uncertainty for the next days. And so this opens the door towards what we call probabilistic weather forecasts. And so here, just before the lecture, I downloaded the probabilistic weather forecast of the ECNWF, so the European Center. And so this is the forecast that started at midnight. And you see for the first day, the temperature, all 50 lines are quite close to each other. There is not a lot of uncertainty. But then later in the forecast, you see that the uncertainty starts to grow. And it's clear that next week will be warmer, will be better. But there is a very big uncertainty, of course, which is logical. Here you see the same for precipitation. And then you can calculate all this kind of probabilistic scores. Next Friday, we have about 25% chance of having temperatures above 25 degrees. And then about 70% chance of having more than 20 degrees and so on. So this is the way that weather forecasts are done today. And this probabilistic information is very useful if you need to make decisions. If you need to decide whether to switch off, for example, your wind turbines in the North Sea, then it's very useful to have chances, to have probabilities. So for many applications that are related to financial or economical decisions or risk management, this kind of probabilistic scores is really a big step forward. Okay, let's now switch to climate modeling. So this was all about weather modeling. If you want to model the climate, you again need a model of the atmosphere, of course. And the model of the atmosphere, that's actually copy-paste from the weather model. And on top of that, you also need to account for other, what we call other spheres, if you want to tell something about climate. And for example, you need the biosphere. You need forests and land use in your model. You need the oceans. You need ice. We need a model for Antarctica, for Greenland, for the North Pole. We need ice models. So there are other components of system Earth that are important if you want to do climate simulations. So if you do climate modeling, we typically say that we use an Earth system model. It's more than just the atmosphere. And the complexity is that all these models that are on its own already quite complex need to be coupled, and you have many feedbacks between them. One illustration, if your atmosphere is warming, then there will be more sea ice melting. If sea ice melts, then the albedo will change. You go from ice to ocean, so there will be additional warming and so on. So you have different feedbacks between all these different systems. And so you see that during the history of climate modeling, the complexity has always been growing. Remember Manabe 67, a one-dimensional climate model. In the 70s, we have three-dimensional climate models where there was only an atmospheric model. Then we added the land, then oceans, then aerosol chemistry, more chemistry, carbon cycles, dynamic vegetation. That means that your vegetation can change when your climate changes, atmospheric chemistry, and so on. So you see that the models today, they have many components and the atmosphere is only one. In the beginning, it was only atmosphere. So a climate model is much more than 1 million lines of code. You have all these modules that are coupled. Now, this is an important slide because it deals with the difference between weather forecasting and climate modeling, and the two are from time to time confused, sometimes by purpose. But it's important to explain the difference. So weather modeling, if you make a weather forecast, weather modeling is actually an initial value problem. You start from an initial state and you make a forecast for the next hours or days. After 10 days, 14 days, you have so much uncertainty that it does not make a lot of sense anymore to continue. So it's an initial value problem. Climate modeling is completely different. Climate modeling is a sensitivity experiment. So if you do climate simulations, then we run the model for 100 years, 200 years. And while we are doing this, we are changing some parameters of our planet. We are increasing, for example, greenhouse gas concentrations. We are changing land use and so on. And then we are not interested in the weather of this experiment, but we are only interested in the statistics of the weather. We are interested in the climate in 2100 or 2200. So this is not at all an initial value problem. It doesn't matter whether you start your climate simulation today or tomorrow or yesterday. It's a sensitivity experiment. If we follow a certain scenario for greenhouse gas emissions, land use, and so on, how does the climate react? So it's a completely different problem. And climate modeling has several very important uncertainties, and it's really important to try to explain that because these climate models, they have a significant impact on lots of policy decisions that are taken today. And I would like to highlight two types of uncertainties in climate modeling. The first one is the scenario uncertainty. So what you see here at the left are the past CO2 emissions. So since 1900 till today, you see that we had a huge increase in CO2 emissions, no surprise. You also see the COVID dip in our CO2 emissions. So this is what we know, that there is no discussion. These are our measurements. But then, if we want to do these climate sensitivity experiments, we need to make assumptions about the future. What will happen in the coming decades? So our climate simulations, they are driven by scenarios for CO2 emissions, for example. And in these scenarios, you can make different choices. And here I show you the different scenarios that have been used for the last IPCC report. And I would like to focus on the red line and the, purple line. So the red line is a very pessimistic future because you see a huge increase in CO2 emissions. This red line is the very famous SSP 8.5 scenario. So very pessimistic. If everything goes wrong, we might have this. And this is the worst case scenario, let's say. Of course, if you use this scenario, you will have a huge warming by the end of the century. Then the purple one is an extremely optimistic one. We immediately start to reduce our emissions very fast. And in the second half, we will have negative emissions. So we will subtract at a huge scale CO2 from the atmosphere. So there is technology that is being developed to do that. So they count on negative emissions. Of course, if you use this scenario, the warming that will come out of our simulations will be much, much lower than in this scenario. But we don't know what the truth will be. And that's exactly why we use different scenarios. So In climate science, we have defined about 5 or 6 scenarios, and all the groups over the world use exactly the same scenarios, such that we can compare our results. Now, in the last 2 weeks, there has been quite some fuss about this plot. I don't know whether you follow that. No, but there was a lot of discussion already for years on the red line. The red line, the highest line, was actually not very realistic anymore. Already for a few years, that was clear, that there was literature on that. And 2 weeks ago, there was a very important paper that came out and that describes the scenarios for the next IPCC report. And so all the modeling groups will use these scenarios. And in these updated scenarios, the red one is gone. And so it disappears. And of course, that creates a lot of questions. Why did we use this scenario? Blah, blah, blah. So it's a lot of interesting discussions these days about scenarios. I would say that it's not so strange that you update your scenarios every, let's say, every 8 years, more or less, because now we have more knowledge about the future. And I think it could also be seen as an optimistic and so a little bit of good news. The worst case scenario is actually off the table now. That was the message that you can get out of that paper. Also, the best case scenario is gone. Also, the purple one is, we will no longer use this one because that's also off the table by now. But you should understand that we can create whatever warming. Depending on the scenario that you take, you can do whatever you want. It's very important to understand that it's a sensitivity. Given a scenario, how does the climate react? So scenario uncertainty. Second uncertainty is the model uncertainty. We have about, I would say, 10, 15 global climate models, Earth system models. And if you take the same scenario, in this case, it's a scenario with this long name. If we take the same scenario with different models, we all have a little bit different outcomes. And so you see this spaghetti of lines for the future, that's models with the same scenario, but with a different model. So it's also important not to base all your policy on one model. That's risky. Imagine that you just by accident have that model that is most sensitive, then you are preparing for something that is actually too pessimistic. Or if you take the lowest one, then you are also significantly underestimating the impact of that scenario. So we always advise to take the spaghetti of all the models and to include that kind of measure of uncertainty in the projection. So this is model uncertainty. So this is the status today, and today at the RMI we are finishing our Belgian climate projections. So by the end of this year, we will present our expectations for Belgium based on model simulations, where we zoomed in on Western Europe with the technique that I showed you earlier. Okay, and I have few minutes left to talk about the future. What will happen in the coming years? What are the trends that we see in weather and climate modeling? First trend, there will be 3. First trend, we are going to higher and higher resolutions. That's not a surprise, you already said it. The bigger computer can lead to a model forecast with a finer resolution. So we see an increase in the resolution. And to demonstrate the impact of an increase in resolution, I would like to take you back to 18th of August 2011. There was the Pukkelpop storm. So there was a downburst over the festival terrain. At that time, the forecast had a resolution of 4 kilometers at the RMI. And here, this red dot is Pukkelpop. So here you see the precipitation forecast for that day. Nothing special happens at Pukkelpop. There is quite some intense rain for the Ardennes. This is the reality for that day. So the radar precipitation amounts. So you see that there were a few very intense thunderstorms that went from southwest to northeast. And then we redid years later the forecast with a new version at 1.3 kilometer resolution. And you see that this new version produces patterns that are actually much closer to the radar image. Of course, this is only one case, but you see that there is much more realism in this forecast than in this one. And so this is exactly because when you move from 4 kilometers to 1.3, you come at a resolution where these thunderstorms, 10 kilometers, are very well resolved. And so you see, if we can push this further to the left, we expect better and better forecasts. Today, in research mode, we are running our models at 500-meter resolution. And so this line will continue to shift in the coming years. If you can shift to finer resolution, you will resolve new atmospheric phenomena. And I would like to show you one other example, because this is a research topic where I have been personally quite active on. So you might know that in cities, it is warmer, especially during the night. So that's the famous urban heat island. And we have a network of weather stations in Flanders, where we monitor these urban heat islands. And there are also a few stations in Antwerp. And for example, here you see a map with the minimum temperature during the night during a heat wave in 2020. So what you see is in the city center of Antwerp, it's pink and purple, which means over 18 degrees or 16 to 80 degrees as minimum temperature. The same night, you have also some blue dots, and these blue dots, for example, here in Contig, they are at very rural spots. Blue means between 12 and 14 or less than 12. So you see, over quite short distances, you have big temperature differences. And this kind of urban heat island effect is relevant for several domains like health. But in the past, we were not able to resolve that. So here is a simulation, 12-kilometer resolution. This is the city of Ghent. You do not really see a nice urban heat island. Same simulation, same city, 2.5 kilometers, you start to see a reddish core. This is the city center of Ghent. So also there, we are gaining more realism of our models. So here, this is research of one of the PhD students in Ghent. Second trend, and you were probably already surprised that I didn't mention AI or machine learning in the first hour, but here it comes. So trend number 2 is that we see a complete new way of making weather forecasts. And it's what we call data-driven forecasts. And this is actually really this was really quite shocking when it happened. So this is very recent. I say it's a trend for the future, but actually it started a few years ago. For example, here in 2023, there was a paper written by people from Google. So people from Google, they used the massive computing power that they have to train a machine learning model called GraphCast, and they trained it on the archive of weather information that we have. So for the past 50, 60 years, we have very detailed weather maps. Based on all this past weather information, they trained the machine learning model, and then they made forecasts with that. And that was the big surprise, the scores of their forecasts were actually very good, because the idea of using that for meteorology was not new. I remember already quite long ago, a professor in our department that was working on a completely different topic, he asked me, yeah, why don't you use AI and machine learning for weather? But in our community, we were actually convinced that that would not work very well, because we thought that we understood the physics quite well of the problem. We have nice scores, and weather is extremely chaotic. So you cannot simply copy a situation from the past to the future. It's more complex than that. So it was quite a shock to many of us when all of a sudden people at Google and NVIDIA and Huawei, because it were all the big tech companies that started with this, came up with weather forecasts, and they were beaten some of our models for some scores. So here I take once more the same score picture, but now I have added the AI models. And what you see is that you have a jump in scores. So this is typically we have a very gradual increase, but since 2 years we have AI models, and here you see the AI model of ISMWF, AIFS, and you see that the score is higher for 3 days, 5 days, 7 days, and 10 days. So it's beating our traditional models for this score. So this was quite a surprise, and I can guarantee you that there were lots of unpleasant discussions when this came out, because we had been working for 70 years on improving these models, and all of a sudden, let's say a very naive approach, machine learning, you don't need to understand anything about meteorology. There is not one physics equation in that model, and they were beating these models. So that came as a shock. But in the meantime, there are 2 important caveats, so to say. So the data-driven forecasts, they can beat physics-based weather models, but first remark, these data-driven models, they are trained on the archive from the past, and the archive from the past is actually built with physics-based models combined with observations. So today, they still need the physics-based models to have good training data. So the data-driven models are still now trained on something that is created with the physics-based models. However, the still is important because a few weeks ago, I saw a paper where they claim to have made a machine learning model that was trained directly on observations. So where this kind of products, where physics-based models are involved, are no longer needed. So it's going very fast. Second challenge for the, let's say, machine learning models is that they perform on average very well, but they seem to struggle with extreme weather. And that's not a detail, of course, because it's on the days with extreme weather that people count on the math services. And so there was a paper 2 weeks ago, was also headline news, it was in the national news. In this paper, they compared the scores of the Google model. Fuji is a Chinese model, Pangu is the Huawei model, and then the European traditional physics-based model in purple. And so you see that the traditional model has difficulties for the general temperature scores, root mean square error, but for the heat records, the traditional one still beats all the other ones. For the cold records, for the wind records, so for all the extreme events, it seems that the machine learning models have problems. And we are doing research where we, let's say, throw away all the extreme events in the training data, and then we ask the machine learning model to forecast an extreme event, and you see that it's not able to do that in a good way. And this is somehow logic, because if it's not in the training data, then the model cannot really produce it. So today, at this stage, they have a problem still with extremes. So my personal guess is that for the coming years, maybe decades, the physics-based models and the data-driven models will exist next to each other. But I must say that it's dangerous to make predictions in this domain, but because it's going very, very fast. But the main advantage of the data-driven models, of course, is that it's cheaper. It's computationally very hard to make them, to train them, but once they are trained, it's a question of seconds or minutes to make a weather forecast. So then it's really peanuts. And then the third trend is that we are moving from forecasting weather and climate to forecasting the impact of weather and climate. So there is a trend to go more and more towards what I would call impact modeling. And I would like to demonstrate that with a project that I am leading for the moment. So here you see an overview of all the heat waves in Uccle, the official heat waves that we had. So since 1900 till 2025, and each bar is a heat wave. The longer the bar, the longer the heat wave. The more reddish the bar, the higher the average temperature during the heat wave. And there are two very spectacular heat waves, I would say. There is one that you all know, that's the 2019, July 2019 heat wave, where we reached the highest temperature ever measured in Belgium. Any guess what was the highest temperature? Our new national temperature record? No? 43? No. It's a bit less. So for Uccle, it's 39.7. And for the country, there was a 41 point something somewhere. So close to 40 or about 40, yes. And then the second famous one is the 1976 heat wave. I don't remember that heat wave. I was not yet born. But this is also a heat wave that was really very interesting because it was a very long heat wave. But also it happened at a time when global warming was quite low still. So if this would again happen today or in the coming decades, that would be really a huge event. So this was, at that time, we think or we estimate that this is an event with a return period of 100 years, more or less. And in more recent years, we did not have this kind of long, intense heat waves anymore. But one day we might be unlucky, and then we will have a 1976 that is, of course, much stronger because now Belgium is a few degrees warmer. So this is the past. And what we now did, what we are now preparing is a tale of a future heat wave. So we are running, I explained to you, we did new climate projections for Belgium, but instead of only presenting the statistics and the trends and the uncertainties, we also would like to present this in another way. And so what we did is we developed a scientific method to select future heat waves. And for this specific project, we tried to figure out how a future 1976-like event would look like. So we go to a global warming level 2 world. Today, the world is about 1.5 degrees warmer. So let's say over 20 years, we might live in a global warming level 2 world. How would 1976 heat wave look like in that world? And so we selected a heat wave from our 1,000 years of climate data for the future. And then we calculated the impact. What would be the impact on the economy? What would be the impact on energy and so on? And then we constructed fake, which is a dangerous word, but we created fictitious newspaper articles based on this future plausible heat wave. And so this is something that is still work in progress, but the coming months you will probably see this in the news, because this is a project where we work together with lots of different sectors to think about whether Belgium is prepared, whether we are resilient for this kind of future heat waves. So this is another way to, let's say, translate climate knowledge that we have into products that can help people to make decisions or to think about how to react if that would happen. Voilà, and I will stop here. If you have questions, you can ask them, of course, later. You can contact me, and if you're really interested, we organize in Ghent, together with the Royal Meteorological Institute, a program, a postgraduate study in weather and climate modeling. And next year we will celebrate our 20th birthday with this program. Voilà, I leave it here. Thanks a lot.
I will ask you to show us that you can take data from show protocol.
Mm-hmm. Mm-hmm.
Still exist or the how do you make a model? This not.
Yeah. We do that. So that's a standard way. So if we make climate experiments, we always start in the past. And so we always, let's say, validate our climate models for the past 100 years. Because if your model is not able to reproduce more or less what we had in the past 100 years, then you know that you cannot really trust, or you can certainly not trust the future. So we always start climate simulations in the past. Yeah.
I have a question about heat zones. To what extent are the models capable today to predict more and bigger appearing heat zones in size larger than the scale of your grids? And you see, for example, around massive data centers like the concentration in Virginia, where they saw that a heat dome was formed, and you can measure the extent of temperature effects up to like 30 miles around. And so these effects generate and are self-sustaining heat domes. Can we predict how long they stay and when they appear?
So just to make sure that I understand your question, so you are talking about very local heat domes related to...
In size larger than the grid size.
Yes, but they are really specifically related to data centers, and the heat that is...
Not only data centers, large cities, for example.
Well,
things like a heat dome sitting there for a week or something.
Well, the term heat dome in meteorology is often used to describe a situation where you have a high pressure system, very stable situation that lasts for many days, and that is also some kind of reinforcing itself. But then we are talking about nearly continental scale situations. So I think in general, well, the advantage of heat, of predicting heat waves, is that heat waves and extreme heat often corresponds with very stable conditions, high pressure systems, and that is something that is quite predictable. So we are, if in terms of heat, you typically have a few days or even a week before already clear indications that we might have extreme heat. And this is a big difference with, for example, thunderstorms, where even on the day itself, there are still significant uncertainties. So I think that these heat wave situations are quite predictable. But we see, for example, in our climate simulations that if we take the observations of the past 30 years for Europe, we see a significant increase in heat waves, and the climate models, they show a more slow increase in heat waves. So that's an open research question. It seems that over Europe, our climate models have difficulties with catching up with the increase in heat waves that we saw in recent decades. That's a bit a different question, maybe. And everything that is local, like heat specifically related to cities, for example, that is urban heat island, that is something that you can start to resolve when you have models at a resolution of 1, 2, 3 kilometers. Then you start to see this at least for our cities. If you have Paris or Tokyo, of course, then a 10-kilometer resolution model will already capture that because these cities are so huge. But for Antwerp or Ghent, you need a few kilometers resolution, and then you can nicely see these urban heat island effects. I don't know whether this addresses actually your question, but...
Yeah, I was also thinking how these effects are being augmented by nearby climate or wider climate phenomena around this zone, because they don't seem to disappear easily once this self-sustaining effect starts. So I don't know how you can predict how long they will remain. taking into account atmosphere around it?
Yeah, well, that's a very specific question, but it's true. Well, these very extreme heat waves, they are typically combined also with very dry conditions in the weeks and months before that. So it's true that for these really big heat waves, it's very important to have, for example, a model where you have a good coupling with your soil model, because we know that if you have a dry soil, that will strengthen heat and heat conditions that can, let's say, make it easier for these high pressure systems to form and to stay. And the other way around, once you're in a heat wave, you will have further drying of your soil. So this, for example, this is one illustration of the fact that if you want to make good, to have a good model, you also need to do something with the soil and the land and the interactions with the atmosphere. So you are right that this atmospheric phenomenon of a heat dome is often related to also other phenomena, for example, related to the soil. Yeah.
There's quite a lot of fuss in the popular media lately about this AMOC, this Atlantic conveyor belt current that actually causes our climate in Europe to be actually a little bit warmer than other regions of the world at this latitude.
Mm-hmm.
They talk about slowing down or even reversal of this current. How serious should we take that prediction?
Okay.
How important is it really in all the climate models?
Yeah, so the question is AMOC, how serious should we take this? It's an excellent question. It's also the talk of the town when we talk with our international colleagues, because they are all confronted, at least in Western Europe, with this question. So I think the consensus today, I'm not an expert in AMOC, but the consensus today seems to be, well, that it is a possibility that this could stop. We know that it happened in the past. It's not impossible. But today, most scientists think that this is something that will only happen when we reach quite high levels of global warming. But in recent years, there are a few groups, there are a few research groups that published work where they claim that it might happen earlier than we thought before. But I would say today the consensus is still that this is not something for the coming decades, that we need a lot of additional global warming to reach that. But not everyone agrees with that statement. So there is a lot of discussion also in scientific community on that topic. Nevertheless, it is clear that this kind of tipping points, because this is one example of a tipping point, there are others. It is very clear that the higher we go with global warming, the larger the risk becomes that some of these tipping points might be reached and that certain systems might stop or reverse or switch or whatever. So these tipping points, I think it should be one very good motivation to try to keep global warming as low as possible. Because imagine now that this AMOC would collapse, that would have a huge impact on Europe. So the world would continue to warm, but there would be one spot on the planet, Europe, where all of a sudden we have much lower temperatures, lower than pre-industrial. So that would be that would have a huge impact on this continent. But once more, consensus is that it is not something for the coming decades, but there is a lot of debate on this. But I would say that that's one good reason to try to keep the global warming under control, because that's not something where you can easily adapt for if that would happen. But tipping points is a hot topic in research and also complex. Why? Because you have there the feedbacks between the ocean, between what happens with Greenland and the atmosphere. So you have the tipping points, you have the connection between all these systems, and that's very challenging.
Yes, you mentioned that the progress in this weather forecasting is mainly due to the fact that your grids are becoming smaller and smaller. Is there also progress in accuracy with which you solve those differential equations?
Yeah, so the progress, you could say the progress comes mainly from two reasons. First of all, better observations. Secondly, more computing power. And then with more computing power, you can do many things. One thing you could do, and that's straightforward, let's say, is to increase your model resolution. Now, I present it here very simple. I say we shift a bit more to the left and then we resolve more phenomena and so on. In reality, if you go to a higher resolution, you also need to make some changes in your model. And you cannot, you need to change some of the signs also in the model. Another important remark here is that this additional computing power has also been used to make bigger ensembles, to create more forecasts with slightly different initial states. So if you have more computing power, you can choose how to use it, let's say. But for example, the urban effects, you need a sufficiently high resolution to resolve the city, but you of course also need the physics that explains the interaction between the city and the atmosphere. So it's not just higher resolution. Sometimes you also need to add new signs in these models. And there are also still, because the main profit that we had in the past 20 years is that we started to resolve this convection, these thunderstorms in an explicit way. If you go from 10 to 1 kilometer, that's something where you clearly make improvements. Now, if we would go from 1 kilometer to, let's say, 100 meters, then we might have make progress in turbulence that could become a bit more explicit and so on. But that's for the coming decades.
Technical question. If you parallelize your computations, do you split up the gate and compute subsections of the gate on the different cores?
Yes.
And then the bottleneck is to interface the boundaries between the gates, between these cores.
So everything that happens on small scales, there you typically collect on cores all the information from one grid column. So you have all the information at the different vertical levels for one point, and then you can calculate what is happening there. For example, convection, cloud formation, precipitation, and so on. So these models, indeed, they collect information from one grid column in one core. And then the complexity is when you need to calculate spatial derivatives, because then you need communication between the different columns. And there are models like this IFS model where you do the computations of the derivatives in spectral space. So where you do Fourier transforms, where you need all the information from a certain latitude circle at one core. So their communication is an important bottleneck.
Still the optimal language to do that?
I don't know. They once started in Fortran, and it's not so easy to start again from zero.
A lot of numerical libraries still have the Fortran at the core. Higher level interface.
Yeah, but there are in other programming languages higher level interfaces. But the heart of at least our model is still Fortran code. Yes.
Okay, I have a feeling, since we're discussing programming languages now, that we can go on for a while, but I suggest that we go to the reception, discuss some more, but let's thank Steven.